Hi, I'm Jansi. I'm going to talk about weak heaps, one of the data structure uh, which is uh, which is defined by Ronald D. Dutton from University of Central Florida Computer Science Department. So basically, a weak heap uses a relaxed or weakened version of the standard heap property for sorting an algorithm. Uh, weak heap tree is a tree in which the value in each node other than the root is less than or equal to the element that is present in its parent node, which has the heap property. So we assume that the maximum heap property throughout. A binary tree with the heap property and with supporting algorithms is often called as heap. And in implementation, nodes which have less than two children appear on the bottom of the two levels of the tree, with those on the bottom level being as far as possible towards the left as possible. So, um, getting to know about what is weak heap from its basics. So weak heap is nothing but a data structure which is defined with certain requirements. So the structure is called weak heap because it is erased by relaxing the requirements of a heap and is a special case of a general heap. So the implementation of weak heap is basically in terms of array, it's like using one-dimensional array, but by using an extra bit per each data item, not each data item, for the whole heap. So one of the important conditions of being a weak heap is that the value of any node is at least the value of any node in its right subtree. So coming to the basic requirements of heap tree, the root of the entire tree, which of the heap tree, should not have a left child. So only for the root, the following tree can have left childs, but only for the root node, we should not have left child. So except for the root, the nodes that have at most one child are mostly are at the last two levels only. So leaves at the last level can be scattered, and last level is not necessarily filled from left to right. So each node stores an element that is greater than or smaller than or equal to all of the nodes which are present in the right subtree. So basically, for any node which is for any node that is left node for a node is called sibling, and the right node of that particular node is known as child. So here we have two different cases, which is a term distinguished parent. So in the case one, so the element on the top is the distinguished parent for the element that is present in the right part of the subtree. For case 2, the element present in the root is the subtree is the distinguished parent for the all three nodes that are present in the right subtree and followed towards the left subtree. So a weak heap is generally formally defined as a binary tree where the value in any node is at least the value of any node in its right subtree. And as discussed, the root should not has left subtree, and nodes having fewer than two children except the root uh, would appear on the bottom two levels of the tree. So weak heaps do not require leaf nodes on the bottom level to be as far as left as possible, nor that the relationship exists between a node's value and the values in the left subtree of that node. So here the condition 2, which is like the root has no subtree, should guarantee the roots containing the largest value, because weak heaps are a variant of heaps and they bear a striking similarity to other variants of heaps. For instance, we can consider general heaps and binomial heaps. So, uh, coming to the representation and storing of weak heap, here we can see we have formed a weak heap as discussed based on the conditions as follows. Root is the largest element and it doesn't have any left subtree, but it has right subtree, which is followed by left subtrees. So this is the way we represent array in weak using array. So weak heap structure can be implemented in a 1D array with one extra bit per data item and can be initialized with n items using exactly n minus 1 data elements. So here we have to consider one more index in an array to represent a weak heap. So the previous weak heap can be represented in array as follows. So basically, so how do we use weak heap uh, to sort the uh, elements present in the heap? So firstly, what we have done is the first step for dividing for sorting the weak heap is we already know that the root element is the largest element in the weak heap. So we have to place that towards the end of the array and then split the weak heap as follows. So basically, splitting the weak heap can be uh, yeah, first we have after removing the root element, we'll be left with the tree from here from 30 onwards. So we have separated the rightmost subtree to as one tree, and then we have further divided the leftmost subtree to again a rightmost subtree and the leftmost subtree which is left with one single element. And then we have from the previous step we have three separate subtrees formed. So we can merge these subtrees as follows. So first, the root node containing the largest value becomes the root for all of this merged tree. So this 33 here is the root node, so we'll merge that with this. And here we have formed two other heap trees by merging the smallest heap trees together. And then here we have taken these are the trees. Here we have 33 as the largest element, so we have considered 33 as the we have to consider 33 as the root node, and we have to make this as the root node for the upcoming merged heap tree. So the smaller root becomes the right son of the larger and obtains as its left subtree the original right subtree of the larger root. So this is the merged subtree after merging from the previous step. So we have to now we have obtained a heap tree altogether again. So again consider the take the largest element here, which is 33, and then place it in towards the right of the array here, and then again we'll be left with a heap tree from 30. So again we have to repeat all these three steps again by separating all the right part of the heap tree and left part of the heap tree, again considering the largest element and following the same steps together. So this would be the final result after separating and merging all the heap trees together and then placing the largest element, which is in the root node position in the array. So we can see that this array is sorted here. So coming to the advantages of using weak heap are, due to the use of reverse bits, we can simulate all of the branch swaps within the array. And the relaxed rules keep us from having to bubble up every time as in a standard heap. So this entire operation of sorting, this can be done in place using that extra array operation. So this is all about heap trees, and thank you. I'm done, bro. ఎన్ని మినిట్స్ వచ్చి ఉంటుంది? అవునా, 10 అయి ఉంటుందా? వాడు నో లాంగర్ 8 అన్నాడుగా. షిట్, టైమర్ పెట్టుకొని ఉండాల్సింది. ఇది ఎక్కడ స్టోర్ అయింది?